Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 17th lecture on the course of Marine Renewable Energy Systems Design, where we are taking example discussion of a floating wave energy converter. And in this lecture, we will focus to discuss on the effect of power and capture width ratio on the overall design example, what we consider now. So this is our reiterative idea of what we are discussing at, looking at a central buoy with floor circumferential bean shaped floats which are connected to the central buoy by a hinge, and we are harnessing the energy from this direction of wave approach. So these are the float geometry what we are looking at. So of course we have not discussed much about the results on torus. I have left it due for a homework on this. So you will try to see, because the connectivity of the torus with radial connections to the central buoy is a big design issue. So we have done this study. Papers will explain you, my textbook also explains you this, but I want you to go through them and learn this as an additional learning exercise for you. So we have been discussing these 4 configurations in detail, out of which we saw that this is far better and superior compared to this, and these two do not have much significant effect, and F3 float receives the maximum energy compared to the other floats, and phase difference is also a very important issue compared to the wave angle approach and the oscillation of this particular device system. Having said this, we now understand that capture width ratio is an important design perspective, and this depends on, of course, the shape of the float. Whereas capture width, the word itself is related to what wavefront the float has compared to the wavelength what the wave approach is having, right. So, we already noted this figure for you for different shape of the floats S1 and S4 through for various periods from 1 second to 5 seconds for different approach angles of 0 degree to 45 degree. We already gave these values for you for an F3 float configuration. For an F3 float with all this configuration, this table already we discussed, and we said that as we go for larger periods, the capture width ratio reduces. Okay, we said that. So, let us look at the figure here. So, now the torus, which also has a result in front of us, gives me the maximum capture width for a very short band of frequency, whereas the other floats gives and operates for a wider range of frequency. So, this is one intuitive information which you will get. The torus designed float are not successful operators for wave energy harvest, though you may say they are direction insensitive. They can be easily connected to the central hub with mechanical systems, with stiffeners, etc., and they can also take care of the yaw rotation in case of asymmetric wave approach angles. All these are positive points, fine, but the efficiency of operation is only for a very short range of frequency, whereas these floats operate for a very wide range of frequency. That is one intuitive hint I want to give you to understand you how we will take forward the research on the torus based shape floats on wave energy converters. Now, let us argue this particular float F3 at 0 degree wave angle at 2 seconds period, let us say at 2 seconds period. So, the frequency of operation is the frequency of the response of the device, okay, the response of the device. So, one can see that S4 configuration, which is this one, okay, is harvesting or enabled to harvest the maximum energy, okay, maximum energy for a wide range of frequency in operation for a specific wave period compared to other floats. The next parallel competitor is S1, the black one, okay, the next parallel competitor. So, S4 and S1 are the good combinations of floats for this chosen design configuration. This is an example study, friends. I am not saying this is the only way you should harvest energy, okay? This is an example study. So, this technology transfer is also available, and in IIT Gandhinagar we have energy research cluster where we also invest on the real time installation of these kind of devices for power harvest on ports and harbour sector in maritime engineering. So, I would request the companies or the investors or the academic and research organizations to come forward to collaborate with Department of Maritime Engineering at Energy Research Cluster at IIT Gandhinagar. I take this opportunity to welcome you. We can make a detailed presentation, we can also discuss technology transfer in detail, and we can carry out extensive and advanced research at our place or at your place, and we request you to please sponsor the research cluster ideas what we have in maritime sector at IIT Gandhinagar at this point of time. So, the capture width ratio goes to the maximum of about, let us say, 27% or let us say 17%, expressed in percentage, about 17%. That is the maximum capture width ratio we get in terms of percentage. The ratio is simply a number, but you can still express in percentage, and that happens at a specific frequency about 0.35. If you recollect the previous lecture, we also identified that the power harvested was maximum at about 0.35 hertz. The P average absorbed power was also maximum at about 0.35 hertz. If you look at that, that was because the capture width ratio is maximum at that frequency. So, one can easily understand, friends, the capture width ratio is closely dependent on or influences the power. I am still saying average power because the power obtained by the study is on a virtual PTO linear damping applied to the PTO. It is not the real damping applied to the PTO. That can be only done when you conduct experiments and measure the damping effects on the central buoy and take that value and apply on numerical analysis and get the results. So, it is an average power. So, we now understand that capture width ratio is a very important parameter which influences the power, as discussed in this journal paper as well. So, now let us look at the capture width ratio configuration for different floats location. So, if you look at the central buoy, if you look at this is my F1 and this is my F3 and F2 and F4, if you remember this configuration for the wave direction, you will notice that the maximum configuration of capture width ratio is on these two floats, okay, whereas marginally lesser for F3 float. So, this is a very interesting idea. Friends, this is where the geometric design plays a role. There are two designs we look at, okay. Let us understand that. There are two designs we are looking at. One is the float configuration, that is S1 to S4. The second one is the float arrangement, that is from F1 to F4. So, both of them put together will help you to get the maximum capture width ratio, which will lead to the maximum average absorbed power. So, that is what we say is the geometric optimization in the whole design. Okay. Having said this, let us now also look at the variation of capture width ratio at different time of the input wave. Okay. So, you will notice that the capture width ratio in percentage for S4 float, or S4 configuration for F3 float. So, we are looking at S4 configuration and F3 float at 0 degrees. We also see at 45 degree, I will show you that curve later. So, you will notice that as the period increases, for an operational range of frequency of the device, the CWR decreases. Okay. So, you need to also tune the device in such a manner, the arrangement of the floats in such a manner that the capture width ratio remains active for a wider range of period of operation of input wave and also for a wider range of frequency of operation of the device. Okay, we are looking at two, the input range of periods of waves and the frequency of operation of the device. You will notice that for longer periods, though the capture width ratio is active, but it is lesser. So, therefore, the power will get affected for a broader range of frequencies. For 0 degree, look at this value at 45 degree, the story still remains more or less similar. Okay. Therefore, friends, if you want to design the system for a short period wave sites, then you must choose the configuration in such a manner that the frequency of operation of the device is highly limited only for this range. If you want to choose the device for long period of wave sites, then the frequency of operation is different. So, friends, this frequency of operation was necessary to choose the PTO damping value. Okay? This is the input wave, this is the operational frequency. So, we understand that the capture width ratio also influences is also influenced by the input wave period, the wave approach angle for the operational range of frequency of the device. Okay? Now, based on this experimental and let us say studies and discussions on frequency domain analysis, let us make certain final comments. What did we learn from the frequency domain approach analysis of the preliminary design of the floating wave energy converter? Let us see what are these. First, what is the influence of float shape on the overall performance? That is the first what we wanted, float shape. We picked up different shape of the floats, S1, S2, S3, S4. We also showed you results of S5, but we did not discuss this much because it was a homework for you to learn. So, we discussed about S1 to S4 in detail. We understood that float with higher radiation damping can radiate more waves. And it will also have increased added mass value, and these two will be used to tune the device. Okay. The second observation what we have is higher exciting force gives more absorbed power. This also we saw. Okay. Since the floats are circumferentially connected, to the central buoy, the capture width ratio, which is dependent on the floats, not the buoy, should be achieved by arrangement of the floats. Okay, not the shape. arrangement of the floats, that like F1, F2, F3, F4. So then one can look for whether should I consider more floats, that's instead of 4 should I take 8, 10, we will discuss that. The next point what we wanted to understand is the wave approach angle. We have seen results with 0 degree and 45 degree. Just for the sake of understanding, was 45 degree has an symmetrical axis with respect to the float arrangement of 4, whereas 0 degree also has, but they have different results as we saw. Okay. Then we understood that the PTO damping coefficients, that is the PTO damping coefficients play an important role to arrive at the maximum absorbed power. We also understood that every shape of the float, that is S1 to S4, has different geometric properties, hydrodynamic properties, and this will help us to choose the optimum range of PTO damping. Okay. The next parameter which will be focused on considering the design is the float diameter. Friends, the study have been also conducted for different diameters varying from 0.5 meter, 0.6 meter and 0.7 meter. Though we have not shown the results at this moment, they are available in the research paper. You will notice that, and it is very easy to observe as well, you will notice that the capture width ratio increases with the diameter. Therefore, it is expected that the higher diameters will help improve absorbed power. But the problem is, when you have a central buoy, when you have a larger diameter of the float, then the interference effect becomes a challenge. So, there has got to be a trade off between what diameter should I choose for what length and what external diameter. So, there is a trade off. Okay? That is very important point for us to remember. So, obviously, the exciting force will also increase with increase in diameter for a wide range of operating frequency. There is no doubt. Capture width ratio also increases with increased diameter for wide range of frequency. These are all more or less obvious statements, but still one has got to verify them with detailed numerical analysis. The added mass effect will also be increased with increase in diameter, and the response amplitude operator of course will also get activated and influenced by the larger diameter systems. There is no doubt about that. So, the third parameter which will also control the design is the influence of PTO damping. the absorbed power. We already showed you the influence of PTO damping with the 3-dimensional variation. So, it is very interesting to note that the average power absorbed by the device, the average power absorbed by the device increases with the increase in the damping coefficient. We already saw that in a 3-dimensional plot. It remains active for a wide range of operational frequency. This also we understood. Furthermore, with increase in diameter, capture width ratio increases, therefore, CPTO will also get increased. Therefore, this will lead to higher power. But interference effect is very important. Is very important. Okay. We have also seen for a chosen range of frequency, of the device, there is approximately from 0.1 to 1.8 hertz. The harness is happening from the range of 0.2 to 1 hertz. So, beyond this frequency, the system should be parked. So, friends, there should be an external lock arrangement, the brake arrangement, where the system will be parked, which is true in even wind energy devices. In case of hurricanes, in case of low wind velocities, the system can be parked. There is a brake. Okay, there is a brake which will not allow the blades to rotate. The system can be parked. Here also, the system can be easily parked by controlling the hinge rotation of the floats. So, we apply external brake to stop the hinge rotation. So, the system will become a rigid body, keep on oscillating, but the power absorption will become the minimum. Okay. The fourth parameter which also influences the design is the water depth. So, now we have different configurations of the floats. We have constant diameter, but one can test this at different water depths of 5, 10 and 15 meters and conduct results, studies and obtain the results of the same. So, one can say that the observation is the hydrodynamic coefficients and the heave response amplitude operator are not sensitive to the water depth change. There is a reason for this. The reason is the diameter of the float, the geometrical arrangement of the float, remained constant. When you do not alter them, then the water depth will not play influence on this. What does it mean? The design can be now implemented and installed at any water depth. I cannot say infinite, but relatively the water depth sensitivity will of course have influence on the exciting force. The system should be designed for that. You know, most importantly friends, as the water depth increases, okay, the mooring tension changes, okay, because you are having a central buoy. The central buoy should be connected to the mooring line. We are talking about a deeper water depth. So, as the water depth changes, let us change this small d. As the water depth increases, there should be check for stability of the central buoy first. Therefore, the mooring tension increases. Okay. This is the water depth. I am sorry, the water depth has to go. Yeah, this is the tension. Mooring tension increases, and therefore one has to check the Matthews stability of the central buoy first before we connect them to the device. Okay. So, this becomes of course an additional check for the designers to ensure that the central buoy remains stable, because the whole harvest happens at the central buoy. So, therefore, the influence of water depth is also equally necessary to check, but that is the point what we have. And friends, just for your information, the capture width ratio also alters with water depth, because the hydrodynamic characteristics of the sea waves change with the water depth, of course. Okay. So, if I say the water depth at 5, 10 and 15 meters could be examined for the damping PTO, which varies. So, one can say that the damping PTO changes with this, and this was about 4.5 in terms of kilonewton second per meter for a scaled model, which goes up to 6.3 in a scale, and the capture width ratio also gets affected at different periods varying from 1 second, let us say 5 seconds. At 5 meter this remains as 210, whereas at 15 meter it reduces to 155. As the period goes, this becomes 25 and this becomes 19. So, one can see there is an influence of capture width ratio and PTO with increase in water depth, no doubt. So, one has got to tune the design in such a manner that it works for a larger water depth and for a larger operational period of the waves. Having said this, let us now understand the summary of this lecture. So, friends, as a summary, we understood multi-body floating wave energy converter with different float configurations. Okay. Then we did frequency domain approach to examine them. We applied virtual PT damping to the PTO. No design damping was applied. Okay. So, now when we talk about the frequency domain approach, the hydrodynamic parameters were obtained using boundary element method and the PTO damping on the power output is varied as a linear damping number in the analysis. Okay. We also said float F4, the configuration of the float S4, which is a bean shaped with close ends, shows higher excitation force and lower mass and volume. Okay. Then we said that the bean shaped floats have higher captive width ratio than rectangular floats. Of course, the discussion does not include the torus floats. You need to do this in example study for yourself. We also said the interface or the interactions between the floats controls the design configuration. So, this can be tuned to use the device in rough seas. Having said this, we also learned that an increase in power absorption happened with the increase in diameter of the floats. The power absorption also increases with the increase in water depth. But there has got to be a trade-off between the cost of installation and the power harvester, because as you go deeper, the system becomes more complex to design and install. Deep water systems are always complex, right? So, friends, we understood that the maximum power what we could obtain, the absorbed power what we could obtain is about 300 watts per square meter. Compared to the input wave, the efficiency is about 37% and the captive width ratio remained as high as 103. So, these are all we could do using frequency domain approach, which is very simple and easy to arrive at such kind of informations. So, friends, the next issue what we have is very interesting, that we want to take it forward. To do this, when I have not 4 floats, but multiple floats, maybe 8, 10, 12, etc., how it could affect the design, what will be the interference and shielding effects of this, how to obtain the real damping on the PTO using experiments. So, we will be able to learn all of them in the coming lecture series of this course, Maritime Renewable Energy Systems. Please stay connected. I think you will love to enjoy and understand the design in detail what we present as an example study. Thanks to Dr. Sricharan and for his extensive research on this published papers, and also sincerely thank for the support systems extended by IIT Madras on conducting these experiments and conducting research. At IIT Gandhinagar, we also have Energy Research Cluster, which works on technology transfer of these kind of designs patented to real-time applications. So, investors and researchers, please approach Department of Maritime Engineering at Energy Cluster at IIT Gandhinagar for more industrial collaboration and research prospects in the future. Thank you very much. Stay connected.